Good morning. It's 9 a.m. here in San Diego, so we will begin the webinar. Thank you very much for joining us. Today's webinar is on fragment screening and linking. My name is Andrew Ori, and if you have any questions after the webinar, please feel free to email or call. During the webinar, you can ask questions using the chat or questions panel in the GoToMeeting dialog window. You can also catch up with previous webinars on YouTube and keep up with ICM news in Twitter and Facebook and LinkedIn. A 30-day ICM-Pro license is available for webinar participants. I will send out more information after this webinar along with a recording of the webinar. Just as I mentioned, on YouTube, you can catch up with the last 4 webinars in this series. So the first one is probably the most important because we skipped some of the steps in this demo because they're covered in this one. So ligand docking with MolSof's ICM-Pro software. This explains how to set up the ligand and the receptor. This webinar explains how to screen and score and millions of compounds to a protein target using virtual screening. This webinar was 2 weeks ago where we discussed how to incorporate flexibility into the receptor by using multiple conformations of the receptor and other approaches. And then last week's webinar was on covalent ligand docking. So you can catch up with these here. So today's topics, we're going to show in Silico how to screen a database of chemical fragments to a protein target using MolSof's ICM-Pro software. Then how to analyze and view the results of a fragment screen, how to sort the table by p-value and score, and then choose the best hits. And then how to cluster and select fragments based on their location in the ligand binding pocket. And then how to visualize the interactions of a lead fragment in example PDB structures. So you'll see that so if you have a decent fragment bound, you can compare it to the PDB to see if it's similar in the way it interacts with the protein. So it gives you more confidence in the prediction. And then once you have a set of fragments, which you may have solved by crystallography or NMR or something, and you want to then link them, we're going to show you how to do that using the 3D Ligand Editor. Just an introduction to fragment-based drug discovery. So it's a method to identify small chemical fragments which will probably only bind weakly to the target. But then the fragment can then be grown or combined with other fragments to produce a higher affinity lead. Fragment screening libraries generally have fragments that are less than 300 molecular weight, log P less than 3, and number of hydrogen bond donors and acceptors less than 3, and number of rotatable bonds less than 3. So this is just like for high throughput screening, you have obviously the Lipinski's rules, and these are a set of rules just for fragment screening library design, but they're just guidelines basically. So there are quite a few advantages of fragment-based lead discovery or drug discovery over traditional high throughput screening. I would suggest there's some great papers out there, so one of them is listed here, and also I would check out the this Practical Fragments blog, which is always up to date with the latest information on fragment-based drug design. So one of the advantages is that you're going to maybe just identify more hydrophilic hits where hydrogen bonding is more likely to contribute to affinity, and then of course you're going to start from a good starting point, from a small fragment, and so you can design better ligand efficiency. And because it's a fragment, you may have with larger high throughput screens with larger compounds, you may sterically block regions of the pocket and never actually sample or be able to bind to that point because the compound's too big. So by fragments you can avoid these steric issues as well. But I would suggest reading more here and here. So in ICM, we provide a database of fragments, which I'm going to show in a minute. So basically, because our fragment database is relatively small, it has been possible to pre-validate the scoring individually for each member of the library. So this allows us to estimate sensitivity and specificity. So for sensitivity, true positives versus true negative rates at any given score that we provide. And so this provides a quantitative measure of confidence that a fragment is a true active and binds in a specific pose in absolute terms, instead of just ranking it against other fragments. So we have a statistical method to do this, and it's all based on experimentally solved structures from the protein data bank, fragments from there. So let's just have a look at this database. It contains 120 fragments. So we need to open ICM. We need to get the graphical user interface displayed. One second. I'm going to close. So you have the graphical user interface displayed. We can then open that database. If you go File, Open, and go to in Windows C Drive, MolSoft, ICM-Pro, and the file is called fragments.icf. So just click on there and open it. Okay, so this has you can see a table with the fragments contained in it. It has other information which we use for scoring of decoys and true scoring, and it also has a list of the PDBs where this fragment can be found as well. We'll see that this is interactive. We'll see that in the results table this is fully interactive later on, so you can click on that and you can view the fragment bound. So we may be interested just to have a quick look at the properties of our fragments. So we can go to chemistry and calculate properties. So we can calculate the molecular weight, for example, log P, and number of rotatable bonds, number of hydrogen bond acceptors, number of hydrogen bond donors, and I think that's it from the so then we have these columns with molecular weight, log P, number of rotatable bonds. So you can, if you're just interested in the distribution of the molecular weight in this database, we can right-click and select that column, and then choose column histogram, and then we can see a histogram of the molecular weight. So it's ranging from less than 90 through to 175. You can make selections here, and those selections are propagated to the table. You may want to combine more than one property, so we could maybe build a plot of molecular weight, for example, versus log P. So we click on this plot button here. It brings up this table. We can just make a plot, and then we can add further annotations to that plot. So for example, we could color the size by number of rotatable bonds, apply, and maybe add a color based on number of hydrogen bond acceptors, and apply. So this plot, as with the histogram, is fully interactive, and you can make selections here. So this is our inbuilt database of fragments, which we recommend to screen first, because it has all the statistics about true positives and true. So it provides a quantitative measure of confidence that a fragment is a true active and binds in a specific pose. So this is inbuilt into ICM. It's in your ICM distribution. So how would we go about screening this database? So first we need to, just going to delete this for clarity. So the PDB we're interested in is called is a CAMP dependent protein kinase with the PDB code 1REK. So go to the search tab, and then we choose, we enter the PDB code, and just click here, so that loads the structure. And you can see the hinge region here of the kinase, the glycine-rich loop here, and the ligand. But for this example, we're not too interested in the ligand, so we can just move that from the object. I'm just going to delete. Also, there's the waters. I'm just going to delete the waters and this additional pentanal het atom. So now we have these two objects: the ligand here and the receptor. So we need to set up the docking project basically in the same way as we did before in the earlier webinars. So we first need to make this into an ICM object. We can discuss. You can view the old webinars to learn more about the options here. But if you're doing this properly, you would optimize hydrogens and asparagines and glutamines. You may also want to be careful about certain waters, but in this case, I'm just deleting. I've already deleted them anyway, so I'm just going to convert it to an ICM object. So once it's converted to an ICM object, it's ready for docking. So you can see now it says ICM here, so we know this is ICM. We didn't convert the ligand, so it still says XR. It's the raw data from the X-ray structure. Okay, so we go to the docking. So to set up the fragment-based screen, we go to the docking menu, and we need to go to New Project. We provide the docking project a name, so we can call it Fragment Example. And then it asks us where we want to save the project. I'm just going to save it to my documents on my C drive. It asks for the receptor object. We know that's A_1 rec. We could run ICM Pocket Finder to find the pocket. Just click here. That identifies you can see it immediately found the kinase pocket shown in blue here, and some other ones, some allosteric sites, but we're not interested in those. So we have the pocket selected here, or you could have just selected the ligand because the ligand's in the correct place, and you can say define site around ligand. Either one of those approaches will work. And so we go OK, and now we make the receptor maps. It just takes a couple of minutes. Less than a minute. So yeah, it's basically making the maps for van der Waals interaction. It's completed already. Electrostatics, hydrogen bonding, and other grid maps for docking. So now you can see we have another extra. So we have the original PDB structure, which we converted to an ICM object. We have these pockets, which we're not that interested in, G pocket. We have the original ligand, which we're not that interested in. And then we have the fragment example _ rec. So this is the protein we're going to dock to. And then to dock fragments to this protein, we need to go to docking and then choose scan probe fragments. Docking effort is the length of the simulation. You may want to increase this to maybe 5 or 10 if you have time. It's pretty quick screen anyway, so you may want to increase that. So it gives you an option to score the number of poses in the stack. So for each fragment you get a stack of conformations, and you can score those conformations. And then you can filter out those that aren't in the top 50 percentile, for example. Then you need to choose the fragment set, and that file that I opened earlier, with the fragments in it, you can just put default, or you can browse and try and find that fragment database in your distribution, but you can just leave it as default and it will find it in your distribution. And then license type, most cases, if you have the license that they provide, you just leave this blank. These are for different licensing options on clusters, but generally if you're just running on a single machine, you can just leave this blank. Then you go OK, and it performs the docking. So I go back to my Okay, so once the docking is finished, we will get a table, as shown here, with the fragment docked. We will have this L means you can toggle the display on and off. And then you have the docking score. But more importantly for fragments is we have this p-value. So it should give you a measure of confidence for that the fragment is a true active and binds in that pose. So the lower the p-value, the better. And also the percentile as well. So I ran the docking previously, so I've got the results here. So I'm going to open Fragment hit this. Okay, so this is the table I showed in the slide as well. So we have the score of this is the docking score. We have n atom, which is the number of atoms in this ligand. This is the number of rotatable torsions in this ligand, so it's 0 for this example. This is the grid energy for hydrogen bonding. This is the grid energy for hydrophobic energy in exposing the ligand to solvent, to exposing a surface to water. This is the van der Waals interaction energy. This is the internal conformation energy of the ligand, the desolvation energy, the solvation electrostatics, and MF score, which is another statistical based docking score, which you could use, but which is used by other people in the docking community. And then we have the more interesting ones for fragments. So we have the percentile, the p-value, so you can sort by p-value. Just click here, and that sorts the column, and the percentile. So if you want to view how this ligand is bound, this fragment is bound, we just single click. Oh, sorry. Just 1 second. I should have pre-made so go docking. I can just open this project and go to, I was going to remake that hit list, and it'll be more interactive. So basically I pre-run this and then go OK, and then I go to docking, make hit. After the docking is finished, after we run the screen, we go docking, make hit list. We browse. We use the project name. We browse, and we choose the object with the fragments here, and you just go OK. And this will make the hit list. It's prepare, and then the hit list will be fully interactive. I saved it previously, and it wasn't linked, so hopefully this won't take too long to build. So in addition to that column with the p-value and the percentile, there's also a column called location, which you can cluster. So you can just look at fragments that are in a particular position in the ligand binding pocket. So the hit list is now made. So it's exactly the same as the one I showed earlier, but so if we click here, it brings it's going to go to display and show elegant ribbon sketch, and it's going to, you see if I click here, it's put the fragment into the receptor object. So we now have the receptor, and we also have the ligand here. So if I double click on the ligand, we can zoom in to that point and see it's making 2 hydrogen bonds with the hinge region of our kinase. So that's the top hit. We can compare that hit with other fragments. So here, for example, you can just use the toggle on and off. Go down to some different. So you can toggle it on and off. It's shown here. So you can also sort by percentile, and p-value. So as I mentioned, you can also, if you're particularly looking for, in our case, maybe we're looking for a fragment that binds to the hinge, or maybe a fragment that binds in that sort of allosteric way away from the ATP binding pocket in this kinase, you can sort the table, you can cluster the table by location. So to cluster by location, you click here, and then you select the column basically, so you can see that's highlighted. Click on the location, and then click on the cluster button, which is this tree button here in the table, and it'll ask you just use the default parameters here. It says descriptors, the selected column only, so go OK. So we have a tree shown here. You can see that these are all colored yellow, so these are all going to be, if we click on here, we can see that these are all the hinge binders. They're all located in the same location here. So the fragment is the yellow, so you can toggle down. So if we go further down the tree, we will find, so for example, this one's going to be in a different location. It's making a hydrogen bond with a residue on the C terminal at the bottom of the pocket. So these three should be in the same position. And then if you want to go further away, we can find other, this is way out of the pocket, so these could probably be ignored. Let's check that. Okay, so it's a good way of filtering out the results as well. We could just maybe select the ones in the hinge here and just delete the others or whatever. So we have the hit list. So basically the p-score was developed. We had a question about how the p-value was developed. So we have the fragment database from the PDB, and each fragment is pre-scored for each member of the library, and this allows an estimation of the true positive and true negative rate for any score cutoff. So as a result, the expected number of false positive binding poses below the cutoff for each particular fragment can be generated, and this provides a quantitative measure of confidence. So if it's and then we can also compare it to the where it is scored. So this is the example PDBs for this fragment. So we can just click on this link and it will load all these PDB structures with this fragment in it. So you can also compare your docked fragment with the PDB one as well. So you can see in the ICM workspace now we have the other PDB structures where this fragment I clicked on is located. So it's loaded one JB0, one LGH, one PRC, and other PDBs with this, which contains this fragment. So you can then compare them individually and check whether your pose makes sense in terms of the p-value and also the score, and also compared with the PDB. We had a question regarding have we performed the screening with larger fragments. We haven't. The only statistical data we have is with that table that I showed earlier, with the one we just docked. But it's possible we could maybe increase the size of that database in future. So this method was developed by Ruben Abagayan and Max Totroff. Ruben's at UCSD and Max is here at MolSoft, principal scientist here. I had a question about the docking thoroughness. So when we docked, the effort here is basically the length of the simulation. It's exactly the same as what was previously known as docking thoroughness. Effort we thought was a bit better, better name for it. So it's the same. Effort and thoroughness are the same parameters. Okay. So yes, I just wanted to show that you can observe the fragment in the experimental structure. So each fragment in the library is linked back to the PDB entries with the complexes of the fragment containing ligands, and the appropriate rotation and translation of matrices are incorporated in the table, so they're automatically superimposed on your docked ligand. Okay, so that describes how you would screen and how you'd rank the hit list. So you may take a selection of these for experimental testing. You may have some lower affinity binders, which would be good in this case, and you may have confirmed the binding pose by crystallography or NMR technique or some other approach, and so you have some lead fragments. So this is the position we're in now, fragment linking. So this feature, you have like maybe a fragment here and a fragment here in your pocket which bind weakly, and you may want to link these two fragments. So this feature finds the best scaffold that can link here, for example, this fragment to this fragment. So to do this, you have to interactively select 2 or more points for connection in the Ligand Editor, and then we search a database of a 3D database of possible linkers. I'll show you the cutting bond image, the button that you need to use in a minute to define where the scaffold starts and where the fragment starts and ends and where you link. So then the linkers are screened against this region, and the best superposition is taken for the original compound and the chemical is minimized. Then the result is returned as a standard Ligand Editor hit list. We're going to look at the Ligand Editor next week in more detail, but we'll be using that now. And you can also predict a linker with the receptor there or without. It depends on how you set up the Ligand Editor. So you can have this as like a region around the ligand to sample, or you can just remove the receptor and just find linkers that will link those two fragments. And then there's certain filters such as energy strain and other filters you can be used for the screening. So in this example we're going to be using the fully interactive 3D Ligand Editor, which was developed by MolSoft in collaboration with med chemists at Novartis, and you can read that description of that paper of the interaction and the development of this tool, as well as many other cheminformatics tools with Novartis here in Journal of Chemical Informatics and Modeling. So the Ligand Editor is a fully interactive tool whereby you can edit the ligand in 2D or in 3D, and then immediately see the effect of a modification on predicted binding. And it's a fully interactive environment, so you can make a change and then undo it immediately, and the history is saved, so you don't have to worry about you can just experiment with different changes. And then you can dock the ligand, minimize it, and covalent docking and flexible docking and other things as well, which we'll cover in more detail next week. But so for this example, we're trying to find a linker. So we go to, I have an example. Okay, so in this example, we have a protein structure, and we have 2 lead fragments that we want to find linkers to. So you just read in the PDB structure, you set up the ligand, you tell ICM which is the ligand using this button here, you tell ICM which is the receptor using this button here, and then the other buttons become activated and you can make modifications, minimize using this button, dock using this button, different visualization properties, and more advanced tools here, some of which we're going to use today. So once it's in the Ligand Editor, we're in this Lig Edit tab. So we need to tell ICM which where we want to join the two fragments. So we take the there's this scissors button. Hopefully you can see it. We just click on that once, and then we click on the position where we want to. You see it's added this arrow, so we want to find a linker that joins here, and maybe we could choose one here. So we're going to screen the linker database between these 2 points. So they go to Advanced. So once we've made these selections, we go to the Advanced menu and choose Find Linker. So these other things we'll probably cover next week, which is Find Linker. And we have inbuilt into, actually you can download from our website, a selection of linkers from different databases. So we have one generated from Drug Bank and one generated from Cambridge database. We could probably provide others if needed, but these are the ones that are immediately available, or you may have your own set of linkers as well. But they need to be in 3D format, have 3D coordinates from the SDF file, and they need to be converted to MolSof's multi-database format, which you can do using the file menu. I can send instructions on that later, but so basically these are all pre-prepared. So you can just download the Drug Bank one. That's what I did for this example. You browse for that file, select it. Then we have some filters that we can use. So each chemical will have a certain strain, and so highly strained ones we can filter out. So you can say I don't want any to report any hits that are greater than 50 value in the strain column, and I don't want any linkers that have more than 5 rotatable bonds in the core, and I also want the linker to be within 2.5 angstroms of the receptor. So you can play around with that distance, or you can just set up the project without the receptor. So you don't set up the receptor, you can just use the ligand. You can also use some kind of pharmacophore filter. So if you had a linker here which you know is reasonable and you want to match pharmacophoric fields, you can just place that here in 3D as an ICM object, and then you can select it from the list, and it will include that pharmacophore as well. I had some more questions, but I think I'll have to get to those at the end. And then we go to OK, and we run the screen. And I have a pre-prepared hit list. So let's go. So once the linker screen is finished, you'll get a hit list here, which you can sort by strain. So the hit list reports the mole ID, which is the ID number from the Drug Bank database that we screened. Oh, it's the index number, sorry, of that database. So this is the molecule with the linker incorporated. So it has our original fragment here, this side, and this side, and then it has this linker region here. It reports this is the ligand that's taken from Drug Bank and incorporated into the as a linker, so you can see where it's added it here. This is the original, and the final one is just the core. This is the core linker region. So you can toggle this on and off by just clicking here, and you can see the ligand. If you double click, it'll make it into the ICM, into the Ligand Editor. So then you can make modifications or minimize or redock that ligand. So there's also a score, so you can sort by score. The lower the score, the better, or strain. So there's a two cutoff difference. If you had a pharmacophore template here, you would get an RMSD value as well. So this is the linker. So with the linkers, it had a question about whether the linker would check for whether the synthesis is possible. Unfortunately, that doesn't. It's not sort of practical to do that as it stands, but it's taken from the linker region. You can see where the original compound has come from, and you can maybe look at that in more detail to determine whether it is feasible or not from the publication for this, or you could compare it to some other database. But yeah, at the moment, the core of this is looking for a linker that's going to link these two by distance and strain, and with a decent low strain, and that's basically the limit of the method at the moment. But so you can browse through the different linkers here. These are the core ones that they use. So that sort of covers what we wanted to talk about today. So thank you for attending the webinar, and we appreciate your support. And please feel free to email or call if you have any questions. The next webinar is next week, which is on the 3D Ligand Editor, so we'll cover a lot of those things in more detail. And then that's followed by the last in this series on atomic property fields, which is a 3D pharmacophore method for chemical superposition and screening. I'll try and answer some questions now, but there's some I'll have to get back to you by email.